Okay, so essentially I'm trying to set out a technique which follows the logic of this example given here. Okay, so we had estimated the value of duration, well, using the classic approach, and we estimate Macaulay duration, and we manually worked out the value of the bond price and the duration, and I had also set that out as a VBA function previously. But then in addition, I estimate a duration using this technique here, where basically I say the change in the bond price divided by the original bond price multiplied by 1 plus the rate of interest divided by the interest being the yield to maturity, or R, divided by M, which would be given here as 1, and that divided in turn by the change in the interest rate would also yield the duration. And as we can see here, the same values are discovered, right? So this estimate, this relatively crude approach, actually can give duration consistent with Macaulay duration. So if we keep in mind what the figures are here for the coupon rate and discount rate and the time period in M, we can go into our function. So it's same, we're basically saying face 7 is 1000. Discount rate, the coupon rate was 10%. The discount rate was 7%. M was going to be taken as being 1 and for 3 years. So let's just estimate. And we get a value here 2.745. Okay, 2.74575. 2.745 and 76. So basically same figures, right? When we look at the output. Okay, so let's verify that then against another example. What if the so we take the example of the duration here. So we had worked it out in terms of the VBA function. We'd worked it out manually, so 4.053919, and then this figure here, which represents again this type of construction. Okay, so let's verify. Let's see if we can recall. So 5 years, twice a year the coupon is paid, and it's a par bond. And okay, so it's 10%, so that's basically the same twice a year, and we're saying it's for 5 years, and just go back and verify that. Okay, we're saying that the bond is going to last 5 years. Okay, so let's run this. When we run this, we expect to get the same value for duration, and the value here is 40539, and we look here and we have 40539, 40539. So okay, we're getting the same figure. So let's have a look at the code and what's going on. So we start off, we set out two functions. So basically this is the same approach I had developed before. We set up a loop where we discount coupons at 1 plus the rate of interest divided by M. and the loop is for the number of I, which we say is equal to t times m. So if t is 5 and m is 2, or in this instance t is equal to 5 m2, so that's 10 periods. So we discount the coupon payments for the given number of periods, 5 years, but payments being made twice a year. And likewise, we discount the second bond, but at RR instead of R. And RR is the same as R, but I've added on 1, 2, 3, 4, 5. So 0 point, and then 5 zeros and 1, which is the same as here, 1, 2, 3, 4, 5. And I get that figure here for this estimation. So basically RR denotes a slightly higher rate of interest, and we discount the coupons again at that slightly higher rate of interest, and then we take this BV1 and add to that the face discounted by 1 plus the rate of interest divided by m to the power of t by m, which is the maturity, and we repeat that exercise for the second bond. And if you like, the BV1 and BV2 are just buckets that pick up the discounted values, and then we pick up the discounted face, and then we basically set out, if you think of this formula here, this formula here is used to construct the change in the bond price divided by the original bond price multiplied by 1 plus the rate of interest divided by m over the change in the rate of interest. And then we return the duration, and when we run that value, so let's stop and run that value, we get 40539, which is the same value 40539, 40539. So this code is an just another alternative approach to estimating duration, and I will post this code just beneath the video clip.